Okay, in this video I'm going to walk you through essentially how to delineate a watershed within QGIS using a DEM file. So the first thing we'll need obviously is our DEM, and there's other videos showing how to download that and bring all that in, so I won't worry about that now. So we have a DEM, we can double check it's in all the right coordinates. So I have units of feet. We're on Oklahoma State Plane North in feet US. And here the pixel size is basically about 2 meters. And that's what, and then here the elevations are in feet as well. So we've already taken care of some of the pre-processing to convert the DEM to everything we need to use American units. Okay. So here's just a DEM file. You can see kind of the creeks coming in, and then I also have a bridge location shape file here that I'll bring in. And let me just change the look of that a little bit. Just double click over here, and then I'll just go to this topo main road, hit OK. There we go. So it shows up a little bit better. So this is our location. You can see the creek coming in. And if we want to kind of verify that on satellite imagery, one thing you can do, so I've already downloaded this, but this Quick Map Services, it's a plugin that you can do. So you can go to plugins, manage and install plugins here. And then I think just type Quick Map Services here, and so you can just check that, and that'll give you all of these, and I'll kind of show you what this is. So you can drop this down, and it has just dozens of openly available sources for background imagery. I'm going to use Google Satellite, and so it'll pop up in the back. We can just turn off the DEM for a second and zoom in, and here we go. This is our bridge that we're wanting to determine the watershed for, and you can see the creek coming through it. Okay, but sometimes it's nice to have this resource just right there in the back, and you can see the creeks coming out of it there. So we'll turn that off for now to save a little time. Okay, so there's multiple steps within this, so this is going to take a little bit of time, but hopefully it'll be clear. So there's a couple major steps within this for determining the watershed boundaries. Generally, we can kind of come in here and look, say this is the creek, essentially, that comes straight in here. We can see how it's flowing. We can look at the topo map and kind of get a general idea, looking at the upper elevations here and seeing how it works. But we want to formally delineate that. So the first thing we need to do is called filling sinks within our DEM. And what that is think of our DEM is a pixelated picture, essentially, and each pixel has an elevation value. Every so often, one pixel will have a value that's just lower than all the other ones around it. Kind of like a hole. Well, if you're thinking about water flowing down a watershed, if there's just a hole right here, then water's not flowing all the way across like it should, and to keep going downhill, it's going to stop at that hole, and it's going to flow backwards into that hole as well. So we want to fill in some of those holes that they're not necessarily errors in the data like some people will say, but just kind of irregularities within the terrain, or irregularities due to the pixel size that just kind of created these anomalies in the data set. So we want to essentially kind of smooth out the surface just slightly, and in that way everything will kind of flow downhill. So to do that, again, we're going to go to our processing toolbox, and we're going to be using SAGA tools. So I'll actually drop this down and show you. So the two main ones we're going to be using are hydrology and channels. So I'll go ahead and break those out. Scroll down. For this one, we want to fill sinks XXL, Wang, and Liu. There's a few other ones, and they work similar to each other, but this is kind of the recommended one. So let's double click there, and our DEM, we just select our DEM file here. Now this one can get kind of important, minimum slope degree. So the minimum value is 0, so the default's 0.1. From some of the work I've done, when I leave the default at 0.1, it creates a lot more, too many flat areas essentially. So basically it's saying that the slope can't be less than that, and so a lot of areas that have lower slopes, it just kind of flattens out. So we want to reduce that, and some of the literature I've read says 0.01 is a decent value, and it's worked the best for me. So and then here we just want to save our output file, and so we'll just call this DEM filled. And again, it's one of these SDAT files that you get when you run SAGA tools, but again, we can export that to a GeoTIFF later. Okay, so we'll save that, and then we'll just hit run. And this can take some time, and it often pops up, but it's not responding. It's running through basically every single pixel within that DEM. So the bigger the file you have, and as we discussed in a previous video, the higher the resolution. So if you have 1 meter versus 2 meter, this can take a lot of time. I have a fairly small area here, so it went somewhat quickly, but again, this can take 10-15 minutes for a bigger area. Okay, so now we have the filled DEM that's popped up on top, and you can see ideally it should look fairly similar. It has filled in some of these areas here. You can see most of those, if we look at our Google map, are actual like lakes and things like that, so that's not going to affect anything really. Okay, and this is the DEM we want to use to create our watershed. So the next step is to come up here, and we want to develop a channel network. And we'll see why that's important here in a minute. So if we double click here, channel network and drainage basins, under the terrain analysis for channels, there's actually tons of options that pop up. We want to put our field DEM here, and you can see we can create a flow direction raster, connectivity, Strahler order. There's actually 2 drainage basins. This top one is as a raster file, and the bottom one is a shape file. And then channels, and that's really what we're after. So I'm not going to worry about these, just let it save it to a temporary file. And then down here there's junctions between all the different tributaries, which I'm not really concerned with. I do like to keep this drainage basins just to kind of have a general representation. They were not the ones we're going to use, but just kind of give me an idea of what's going on. So I'm going to save these channels to a file. I'll just call it channels, and this is just a vector shape file, the polyline file. And in the drainage basins I'll do the same thing. And again, this is just a vector polygon shape file. Okay. And here the threshold, that's the default value. The minimum value is 1. I think this is based on Strahler order, but it more affects some of these other ones here. So we'll run that. And again here, this is really the tool that requires you to resample. I mentioned filling the DMs that you might want to resample, but on some of the bigger files I've had, even at 1 meter, the fill sinks works fairly well. It still takes a while, but it'll work. But this channel network and drainage basins will definitely crash if you have too large of a file, too large of an area, too high of a resolution. Because all those things we unclicked, the flow direction, the connectivity rasters, all those, it still makes those, and it saves them as temporary files, but we're just not saving them to a file. So it's still doing all that in the background, and it still takes a lot of processing time. So that's another reason to resample and to do around, I think a 2 meter raster works fairly well for most of the sizes I've used. And I think the largest watershed area I did was about 30 square miles. So it was almost 20,000 acres. So, it's a fairly large area, but it worked okay at a 2 meter resolution. So much bigger than that I would mess with too much unless you have to, or I would resample even to a lower resolution. But all right, finally. Okay, so now we can close that. And again, all we saved were the drainage basins and the channel. So you can see our channel network running through here, and our drainage basins, which is fairly messy right now. We'll just click out of the drainage basins, just kind of use those for reference. I'm going to bring this up so we can see where our bridge is. Okay, so you can see we basically developed our channel network here. And so you can see it's just kind of crazy at the moment. And we're not really going to use this too much, but what is really useful here, we want to know, I'll turn that satellite off, essentially right where the channel's coming in for our watershed. And this will be really important for the next step. So now what we want to do is calculate the upslope area. And so I'll just show you that tool. So again, this is under the SAGA tools, Terrain Analysis Hydrology down here. Okay, so we needed this elevation from the field DEM, so we needed that to start with. But there's nowhere to put in this channel or anything. But what this gives us is very specific XY coordinates, and that's what we're looking for. We essentially need the exact cell within this field DEM for the channel, if that makes sense. I'm going to click out of, or just zoom in here. So basically you can see kind of there's a few little sub channels coming in, and what I'm going to do is click on right down here, but I want to know the coordinates essentially right here, and so everything upslope of that will be my watershed area. You can see down here it kind of gives us coordinates, but it's not exact, and we don't know exactly where we're at. So one tool that can help us find that is called the coordinate capture, and it's a plugin we can add. So we'll go back up to plugins, and let's see, type coordinate. Okay, and this actually pops up here. Okay, so you click on that and it actually pops up right over here. So what we want to do is come over here, start capture, and now we basically have an icon that we can select our coordinates. So let's just zoom in pretty tight here, and then we want to select basically right on this line. So now here we have a couple set of coordinates. If we look over here, so here's lat longs for it, and you can set the essentially the projection to use for the coordinate display, or you can come down here, and this one, it's not popping up, but this one should be the coordinates for what your project is in. And if you brought in your DEM with the right coordinates first, that's what they should be in. So here it's just presented as XY, so we want to just copy those values right into here. Okay. Okay. And that's all we need to do right here. We can leave everything else alone, except we want to save this to a file. And we'll just call it Upslope Area. And again, this is a raster file, which is the s.dot file. And generally, this one shouldn't take near as long as the last couple of tools we used. And this is where it becomes really important of getting that coordinate right along the channel, because it's using the same rasters that we use to create the channel. So if you just happen to click over here, even though it's very close, it's probably thinking this is something completely different, and it won't necessarily capture right on here. Okay, so now it gives me a raster that's basically 0 or 100, and so you can see 0 is in black and then 100's white here. So we're really zoomed in, so let's zoom back out. Okay, so now you can see it's starting to make a little bit more sense. So you can see the white area is essentially our watershed. Everything coming into this point. So let's kind of get rid of these channels. I'm going to turn on the satellite and then kind of make this upslope area a little bit transparent so we can see what's going on. Okay. Oops. Well, you can see here the DEM. You basically got your main channel and all the wings coming out of it. And same thing on the satellite imagery. So that's essentially the watershed area that we're looking for. Except right now it's in a raster format, which is a little bit unwieldy for us to use. So we want to actually convert this to a polygon. So the way to do that is come up to raster and conversion, and we want to polygonize or go from raster to vector. Okay, and we want to do the upslope area. It's only got one band, so that's fine. And then we just want to create a vector. So this, I like to work in shape files. That you can see there's tons of different types of files you can use. But shape files will work back and forth, whether you're using ArcGIS or QGIS. So I'm actually going to name this Watershed. Okay, because this will be our final watershed shapefile. Save, and then just run the algorithm. And it should just take a second. Okay. So now we have this big blob, and you can see the border here. But again, it brought in the entire raster, not just that area. So we need to kind of trim this down a little bit. So what we want to do, it named it vectorized, but again, this is our upslope area. This is just the temporary name that QGIS gave it. Alright, but you can see the file path here. So we want to open, so right click, we want to open the attribute table. You can see here, again, there's a 0 and 100, so it's basically created two polygons. One for the outside and one for the inside. Every once in a while you may get a few more extras just because there's tiny little spots within here, but here we only got two. And the way to figure out which one is which, you can just click on either one or two and it'll highlight in yellow which one. And so we essentially want to delete kind of the outside area. The easiest way to do that, if you come over here to the pencil, you can toggle editing and turn on editing. And so we want highlight yellow here. Okay, and then come up to the red trash can and delete selected features. Okay, and there we go. And then just hit the toggle editing and save our changes. Okay, so now we just purely have our watershed boundary. Just to help visualize that a little bit better, we can come up here and just select the blue outline, and there we go. There's our watershed boundary. Okay, so we've created our watershed. There's one last thing we want to do with this watershed, and that's to figure out, well, how big is it? What's the area within this? So come back here to our attribute table, and we basically need to create a couple new fields that calculate the geometry for this feature. So the way we're going to do that, if you come over here, there's this little tool here. It's Open Field Calculator. Click on that. And essentially this is a calculator that provides a lot of different operations that you can add in. And so you can see multiple mathematical things, geometry, different things. What we want to do, we want to create a new field, and we're just going to call this area in feet squared. And I'll explain that in just a sec. So we want decimal number real. So that way basically it's a floating point number that has decimal points essentially. Okay, so down here we can write our expression for this new field. And what we want is geometry. So click on here, and we want area. There's a couple different options. This one with the $sign does a few weird things with the ellipsoid, and it'll really depend on what your coordinate system is set up for how accurate it is. I don't like to use it. This basically is more plain metric and assumes kind of, for the most part, a flat area within your coordinate system. And it seems to be more accurate. So if you double click on area, and you can see it basically opens a bracket and it's wanting you to put something else in there. So we need to tell it the area of what. So let's zoom down, and now we want $sign geometry because it's geometry of the current feature. Okay, and then we just need to close the brackets. So our new field named area in feet squared will be calculated with the area of the current geometry, which is our watershed boundary. Hit OK, and here we go. One thing, this generally is great, and we can do a lot of things with this. Within the USGS regional regression equation for calculating watershed or flow rates, it likes to have the units in square miles. So we can calculate that separately, but we can also calculate it within QGIS and have a column associated. So anytime we bring this watershed up, we can just have it right here. So we'll go back to the field calculator. And so now we want to create a new field again, and we'll call it area in miles squared. Again, we want a decimal number. And this time what we want to do is basically just tell it to convert it. And our equation, we hit fields and values, and we want the field area feet squared, which is this one right here, this number, and we want to convert that to square miles. So assuming this number I have is right, we want to multiply it by 0 point, and there's 7 zeros here. 6, 7, 3, 5, 8, 7, 0, 0, 6, 4, 3. So that's the number I have. You might double check that, but so we just are multiplying it by a constant. We hit OK, and now we have the area in square miles. So we want to toggle editing, save our edits, and now we have a watershed delineated for our bridge here, and we have the measurement for the area. So that'll be it for this video. In the next video, I'll show you how to calculate the channel and determine the elevations for the channel, which are the rest of the equation for the regional regression equations.